In this video, we're going to discuss streamlines, pathlines, and streaklines. And so you guys are at least should be somewhat familiar with a streamline. And now we're going to discuss those in a bit more detail. And so what a streamline is a streamline is defined to be a line that is tangent anywhere to the instantaneous flow direction. Okay, and so that is, if we draw a vector field like I have here, essentially to find a streamline, all we need to do is connect the dots with the vector field, and the direction to the next dot is defined by the direction of the velocity vector. So, in other words, if we have this vector field here and we want to graphically find the streamlines, all we have to do is pick a starting point and then go in the direction of the arrow. And so we would go up, and then it's starting to curve, and then we start to follow the arrows kind of like that. And to find a second streamline, we would pick another point and then basically follow the flow. And so all of these red lines here are streamlines. And so that's great graphically, but how do we find them mathematically? Okay, well, we use the strict definition, and that the equation for a streamline for this box here is given by dy dx for the streamline is defined to be in the direction of the velocity vector. And so the slope of this line, the change in y divided by the change of x, is defined to be in the direction of this velocity vector, or basically the ratio of the height of this velocity vector to the horizontal distance. And that would be the y component of the velocity vector divided by the x component of the velocity vector. So if you want to mathematically find the streamlines, this is the equation that you have to solve in 2 dimensions. In 3 dimensions, you have to solve 2 more. And that would be for the slope in the z direction as the change of height in the z direction as a function of distance along x, and also a distance along y here, okay? And again, but all these formulas are fairly generic, so if you are looking for a slope in the z direction in the numerator, you pick the z component of the velocity in the numerator for the right-hand side, and if you pick and for the change of length in the denominator, you pick the same component of the velocity vector. Okay, so but these are the 3 equations that you would solve. In this class, we will only be doing by hand 2D. So, for example, say we are given this velocity vector field here, where the velocity vector is v naught over L x I hat minus v naught over L y j hat. So here's the example, and we want to find the streamlines for that. Okay, so we're given a nice mathematical function, and so we are given the velocity vector. And notice that this flow is steady, and we know it's steady because none of the velocity components are a function of time. They are only a function of space. Basically, where we are in this box, they are not a function of time. And so we want to find the equations for the streamlines and sketch. And so here we use the definition of streamlines in 2 dimensions, and that's given by this equation here. And so we have dx dy equals v over u. Okay, well, we can look, so that's the equation that we want to solve. It's a differential equation. But now we're explicitly given u, which is v naught over L times x. So we know that u equals v naught over L times x. And v, the y component of the velocity field, v equals minus v naught over L times y. Okay, so now we basically take u and v and stuff it and then stuff it into our equation for the streamline, and then so substituting, we have dy dx equals v, which is minus v naught over L y divided by u, which is v naught over L times x. Well, the v naughts cancel out, and this just equals dy dx equals minus y over x. And so now we have a nice ordinary differential equation, and we need to solve it. So need to solve the ODE. Okay, and this is a separable first order ODE. So it's pretty straightforward to solve. And then we have, we can separate, so we can divide both sides by x and multiply both sides, or divide both sides by y and multiply both sides by x. And doing that, we have dy over y equals minus dx over x, and then we just basically integrate both sides and then not forget about the constants. So the integral of dy over y equals the integral of, that's a really bad integral, the integral of minus dx over x, and integrate, so this implies that the log of y equals the log of x plus some constant, and I'll call that c0. Or going through some algebra, and that should be minus ln of x, sorry about that. Or we have ln of x plus ln of y equals c naught, or we can exponentiate both sides, and we have e to the log of x plus the log of y equals e to the c naught, which is still just a constant. And so I'll just call that another constant, c. Okay, because e to a constant is just a constant. And this is e to the ln of x times y, which is just equal to xy. So the equation for our streamlines, is x times y equals some constant. Okay. And so basically what this equation means is that there isn't just one streamline, there's a whole family of streamlines. And we can pick the streamline by basically changing the constant. And if you want to choose what this constant is, again, this constant is equal to x times y. So all you need to do is pick a point, x, say, if you pick a point, say x and y here, we know that the streamline has to cross through that point, and x times y is equal to a constant. And so that's equal to some x naught, a y naught, that we choose that streamline to, the streamline to go through. Okay, and so for this flow field, if we plot the streamlines, this would be y and x, the streamlines would actually look something like this. And these are all different constants. Okay, and we choose this constant by basically picking a different starting point for the streamlines. Okay, and so that's usually, for the problems in this class, that's how you'll be able to find most of the streamlines. Occasionally, the functions for u and v will be complex, and you'll have to use MATLAB or something like that to actually integrate the ordinary differential equations. Okay, and then also note that streamlines are instantaneous, that basically if the flow field is a function of time, these streamlines are valid at one time instance only, and I'll discuss that a bit more later on. Now, something you may not have, that you have less experience with, are things called path lines. And a path line is a line traced by a fluid particle. And what I mean by a fluid particle is a glob of fluid that is basically tagged, and here we're just following a round. And we're going to be talking about fluid particles all the time. It's just a concept. It isn't an actual particle in the flow, but it's just a glob of fluid that we're going to tag, and we're going to follow it around, and later on we'll follow it around and conserve things. But for right now, we're just going to follow it around. And so if we follow a chunk of fluid as it is moving around and basically track its path, that is what a streamline or what a path line is. And so one way that you can think of a streamline, if you consider this slug and it's moving on your concrete floor or something like that, there'll be a bit of a sort of a disgusting slime trail that is left behind. Well, that slime trail left behind a slug is a path line. Okay, and then how this is done experimentally, how you find a path line, is you have some sort of a channel where you're doing an experiment, and we'll have some sort of incandescent sort of dropper, and as this sort of droplet moves down the channel, it'll sort of leave a trail behind it. And then that trail that is left behind by the glob, by this dropper, is called the path line. Okay. And then path lines can be found by considering the motion of a particle in the flow field, and we're going to assume that this particle has the velocity of the fluid. Okay, and so from rigid body dynamics, to find the path line, all we need to do is basically solve the equations of motion for the particle. Okay, just using rigid body kinematics. So for that, we know, since we're defining for the path line that the sort of fake fluid particle is moving with the fluid velocity, we know that its change that the time rate change of x position of that particle is given by the x component of the velocity field, and we know that the change in y of the particle with respect to the time is equal to v, and the change in z with respect to the particle, or with respect to the time for the particle, is given by w. And so basically, to find the path line, we basically solve the equation of motion for a particle for its x, y, and z positions, and then basically just query and just basically plot the position of that particle as a function of time. Okay, but in general, we have three coupled ordinary differential equations, and they're not always the easiest things to solve. For some of the problems in the book, we can solve those, but often you need to go to the computer to solve them. Okay, and so I will discuss what a path line is in a bit more detail later on, and a streak line is also a line that is made by considering the motion of a fluid particle like this, but instead of tracking the position of one particle, for a streak line, we basically make a line by joining particles emitted from one location but at different times. And so one way that you can think of a streak line, if you consider a marathon or some sort of racing event, where basically they have one car go, where they basically have one car go, and then car one goes, but then all the other cars are basically being held back. And then they basically go one after the other. Okay? And so basically car 1 goes, then car 2 goes, then car 3 goes. Now if you had a drone and after the race got going, you would see that car 1 would be up here somewhere racing, car 2 would be over here, and car 3 would be somewhere over here. And if we picked a line that connected these cars, that would be a streak line. And so in an experiment, how a streak line is made is, instead of just tracking the position of one droplet, we basically have an eyedropper and we drop many droplets. And then we connect the line that is connecting all of the individual little droplets at a given time. So basically we have our drone and we are basically looking at the position of, and then at some time t we take a photograph, and then we connect all the dots for all of these little droplets. Okay, but in general, since we're just considering the position of various particles, you still solve the same ordinary differential equations to get the particle position, but instead of following one particle, you follow a bunch of particles that are released from the same point, but at different times. And then you just connect the dots with the different particles. Okay, and then the third related one is called a timeline. And I briefly mentioned that in another video. And a timeline is a line that is connecting nearby fluid particles at an instant of time. And so I showed this GIF image earlier because this is a computational fluid dynamic video of the flow in an array of wind turbines, and these little white wispy things that you see right there, those are timelines. And so this here is a timeline. So we have to define a timeline, we basically pick at an instance of time, we basically pick a whole bunch of particles here, and we release them at the same time. And instead of tracking the path of where each individual particle moves, we instead look at how that basically look at that line of particles, and how does that line, if you connect these different particles, change with time. And so here, if we have our little channel and we want to make a timeline, is we have, say, not one eyedropper, but we have, say, 5 of them. And if the velocity profile in this tube looks something like this, you would expect the flow to be faster in the middle of the tube than towards the walls. So at time equal to say 0, our timeline looks like that. Now, if we release the particles and they move downstream, this one in the middle is going to move out the furthest, and these two the second slowest, and these two the slowest. And so if we plot the position of the particles, they will look something like this. And the timeline is just the line that connects these particles. And as time goes on, the bump in the middle becomes even more exaggerated, but we still find the timeline by basically playing connect the dots. And these are very, very useful because, like I said earlier, these timelines are revealing that in the wake behind the wind turbines, the velocity is slower, and these particles lag. But in the channels between the wind turbines, where the fluid velocity is much higher, the particles basically keep on moving like they didn't see anything. And so basically, and again, we're still considering the motion of particles. It just is dependent, and so the difference between pathlines, streaklines, and timelines are basically revolve around when we where we release the particles, how many particles we release, and then how we basically plot them. For a pathline, you plot the sort of position as a function of time for one particle. For a streak line, you release a bunch of particles from the same spot at different times, and then at some time t, you take a photograph, and then connect the dots. And then for timelines, you release a whole bunch of particles in a line, and then basically follow that line. Okay, and again, these can all be found by solving the same ordinary differential equations to find the position of a particle as a function of time. But for pathlines and timelines, you have more than one. Okay, but in general, to find pathlines, streaklines, and timelines, we need to solve the equation of motion for a particle or multiple particles. So for dx dt, we solve this equation here, where dx dt for particles equal to the x-component of the velocity, and our initial condition is some at x0, we have x naught. And similar for dy dt and dz dt. And so now to be a little more explicit here, so for all three of them, we basically solve these ODEs here. And now how you do this with pathlines, now basically how you use this, basically how you use the solution to this. To find a pathline, what we do is you consider one particle that is released at time naught from some position x naught, z naught, and y naught. Okay? And then you plot that, and then you plot the position of that particle as a function of time. So then again, you just solve this ODE here, or the system of ODEs. And you just plot the position, the xyz position or xy position in 2 dimensions of the particle as a function of time. And now for streak lines, we have multiple particles that are released from the same position. X naught is at position x naught, y naught, and z naught. But now, instead of releasing one particle at some t naught, we release multiple particles at time t1. And at some later time we release particle 2, and then at another later time we release particle 3, and then at some later time we release our very last particle Tn. Okay, and so T1 is the time that we release the first particle, and Tn is the time that we release the last particle. Okay, then we basically solve the equation of motion for the particles to some time t, and we're going to solve we solve these differential equations for all particles to the same final time. So they start at different times, but we are basically asking, say at a time of 2 seconds. You ask each particle where it is located, and then you basically connect the dots with each particle. So as an example, this is going to be a more complex one, but it has a nice little animation, so I can hopefully show you what a pathline and streamline is. So we are given the velocity of vector u is x times y, and v is minus y times t. And we're to find the pathline in streak lines for particles that are released from x naught equals 0.1 meters and y naught is equal to 3.5 meters at a time of 1.4 seconds. Okay, now in general, so again, we need to solve the equation of motion for particles, for an array of particles that are released at 0.1 meters and y of 3.5 meters. And so the solution, we solve the equation of motion for each particle, but what you'll find when we go through it is that the equation is you need to use MATLAB to solve it. You can't do this by hand. Well, you can, but you need to use some special functions. Okay, and so we do that like before is we consider an array of particles, and so the time rate change of position for each particle, and this is just for particle I, it could be particle 1, 2, 3, 4, 5, is equal to u of the velocity field, which is equal to x times y, and similar for the time rate change of y for each particle. And the initial position of the particles is given at x equal to 0.1 meter and y is equal to 3.5 meters. And we then solve this system of differential equations from the release time of each particle to the final time, which is 1.4 seconds. Okay, and so for the path line, we just release a particle at t equal to 0. So and so if we track the position of that particle as a function of time, we have the path line. Now for the streak lines, we have to pick a number of particles and release them at different times. So we basically solve these ODEs for a whole bunch of particles. Here I just pick 8, and I'm going to release them every 0.2 seconds. Okay, and so basically TI, the release time for the first particle is 0. It's released right away. The release time for the second particle is 0.2, and so forth all the way to the last particle, which is released at 1.4 seconds. Okay, and so I use MATLAB to solve this. I'm not going to go through the code in detail, but you can see all I literally do in this code is I basically define 8 particles, like I said, and I define the point where we release the particles, and then I define the times at which we release the particles here, and then I just loop over all the particles and a whole bunch of time points, and I basically solve this equation of motion using MATLAB. And numerical methods is not a prereq for this class, so I can't assume that this does, but basically what this code does here is it just solves for the x-y position of each particle at the same time. Okay? And so for those of you who are interested, here is the code. This is a function that actually solves the differential equation. So this evolves the position of each particle, and it uses MATLAB's ODE 45. And a little caveat is that it will is that if the time is less than the release time, then we don't move the particle. Okay. Then after we define and then we need to define the right hand side, and so this is just dx dt, which is x times y, and we have dy dt, which is minus y times time, which is exactly how I have it defined above. Okay. So if I go do that, for those of you who are interested, you can I will provide this this MATLAB file so you guys can mess around with it. But if we let this go, we have 8 particles. They are released right here, and this here is the evolving path line of first particle, particle 1. This here is the second particle. This here is the third particle. This here is the fourth particle. This here is the release of the fifth particle. This here is the release of the sixth particle, the seventh particle, and the 8th particle. Okay, and so here we followed the motion of particle 1, and that was the path line. And I'll let this play through again. And notice that the velocity vector, which I have drawn here, it's a function of time, and as time goes on, it keeps pointing more and more downwards. And because of that, these particles don't all follow each other perfectly. Okay, and so just let it play through again. And because of that, the path line or the streak line, which is right here, and the path line, which is here, are basically different. And each of the particles, because the flow field is evolving, they each took a different path to get to their final position. Okay, and so using the trajection of all these different particles, we can find the path lines and the streak lines. And you can see at the end of this, to find the path line, we basically followed this particle here, and to find the streak line, we just played connect the dots. Like this. Okay, and so that's the streak line. Okay, and now we can do the same thing for a timeline, but for the timeline, instead of releasing a bunch of particles from the same point at different times, we release all particles at the same time, and we basically just have a line that connects these different particles. So you can see here how the timeline of the particles is evolving, and these lines here are the path lines for each individual particle. And so we can see how the timeline evolves with time. Okay. Okay, and we can also find the streamlines for this velocity field. And so to find the streamlines, turns out to do that, we can do that one by hand. So dx dy for streamline, or dy dx I should say, for streamline, recall that is equal to v over u. Well, we know that v equals minus y times time divided by x times y. The y's cancel out. This equals minus t over x. And so now, to find the streamlines, notice that there's a pesky time here. And recall that streamlines are a function of time, are valid at one instant of time. So to find the streamlines, we need to pick a time t. But if you can integrate it by hand, I really suggest you don't pick time t and then integrate. I suggest you integrate it with that time there. But it is not a variable for the ODE, and so as far as for solving this this differential equation here, time is just a constant. Okay, so we have dy dx equals minus t over x. And this is a separable first order ODE. And we can solve this. It's first order separable. So we have dy equals minus t dx over x. And we can just integrate this. And so we can integrate this from y naught to 0. Dy equals x naught, which is just some initial position of the streamline, minus t dx over x. And if we solve this, this implies that y will equal to y naught, if you just go through the algebra, minus t, the natural log of x over x naught. And of course, in your homework, I would expect you to show your work. Okay, this is a first order ODE. You can also use it. You can also solve it the sort of more standard way, where you would have y solve the standard way. Where you basically do the integrals, but you wouldn't put the bounds. And instead you would have y equals minus t ln of x plus some constant. and then you just solve for the constant. It's to find C, make the streamline pass through x naught and y naught. Okay, you basically force the streamline to pass through a point, and that's really bad. Okay, and so if we plot this, these streamlines, all these individual lines here are all streamlines, and this is just the streamline evolving as a function of time along with the vector field. And so you can see that for this vector field, which is fictitious, it is changing as a function of time. Okay. So what if the flow is steady? What happens if the flow is steady? So here, these were transient flows. It was a function of time. And because it was a function of time, the path lines and streak lines and streamlines, for that matter, were all different. Every last one of them. But what if we made the flow steady? What would happen if we made the flow steady? So let's, motivated by the previous example, let's choose u to be x times y, and let's just get rid of the time dependence on the y component of the velocity and just make it equal to y. And let's just use the same code, but all we do is we just change our function here and just get rid of that time right there, and then basically rerun the code. And if we rerun the code, what you will find is that these velocity vectors don't change as time, so the velocity field does not change. And what you'll find is that the position of each particle follows the exact same trajectory. And the reason each particle is following the exact same trajectory is that the velocity field is not changing. Whereas with the previous example, each particle took a slightly different path, and that's because the velocity was changing as a function of time. Okay. So then, now I gave you these examples and I showed you at least one way, but in general, how do we find path, streak, and timelines? So how do we do that? Well, if it's simple, you do it by hand, and I'm going to do it, and I'm going to give you an example here in a few minutes, where you basically solve these differential equations by hand in 2 dimensions. There aren't many flow fields where you can do that nicely. A lot of times, these differential equations are nonlinear. They're a function of time, and you just can't do it by hand. And the alternative, which is what I did for the above examples, is you can use something like MATLAB if the velocity field is a function of x, y, z, and time, if that's known. And so that's how I did the above. And the one you're most likely to do if you're to compute these is, and I'll discuss this a bit later in class, is you can use computational fluid dynamics to compute the velocity field as a function of space and time, and then you can basically track little you can track what are called tracer particles, and tracer particles are just particles that move along with the flow. And that's exactly what was done with the wind farm calculation, where basically they did a big massive supercomputer simulation of the flow going through all the wind turbines, and then they basically released a bunch of little tracer particles and then followed them around to define a timeline. Okay, and so now we're gonna do a simple-ish example by hand. And so here it's going to be the same velocity field for the streamline that we did by hand, the first one. where v is equal to v naught over L x I hat minus v naught over L y j hat, and L is 1 meter and v naught is 1 meter per second. Okay, and so here v is equal to v naught over L, and v naught, and we are given this field. And again, this is the homework format I want you to follow, so please follow it. Just write the given, find, and the solution procedure. And so here we're to find the path lines and streak lines. And note, it's steady, so the streamlines, path lines, and streak lines are all the same. And so if steady, path lines, streak lines, and streamlines are all identical. Okay, and so if I really wanted to, I could stop here, but I'm going to go through the motions as if they were all different and sort of show you that for the special case that if the flow is steady, and only if it's steady, the path lines, streak lines, and streamlines will all be the same. Okay? And so the solution here is we need to find the position of a generic particle released from some initial position at some release time as a function of time. Okay, so that is, we solve dx dt for particle equals u, and that equals v naught over L times x, because that is the x component of the velocity. And we have the initial condition, x equals x naught at t equals t naught, which is just some release time. Okay, if t is less than t naught, we hold the particle. Okay, and then we do the same thing for y. We have dy dt for the particle equals v, and that equals minus v naught over L times y, with the initial condition that y equals y naught at t equals t naught. Okay? Or dx dt. Now that we just understand that it's for a particle, I'm just going to drop that. We have v naught over L times x, and dy dt equals minus v naught over L times y. And both are first order separable ODEs that are uncoupled. And what I mean by uncoupled is that you don't need to solve both of these differential equations together at the same time. You can solve one and then the other. That is, the solution of one does not depend on the other. In general, that is not the case. All I would need to do to mess that up is to put a y here and maybe an x squared here. And then all of a sudden you need to solve them together, and you need to go to the computer or use some very, very fancy math techniques that we're not going to even think of getting into in class. Okay, but in general, the solution procedure for each of these ODEs, they're separable and they're the same, and I'm just going to go over the x1 in detail. And again, in your homework, I would expect you to show full detail for all of them. Okay, and so we solve, and we have dx dt equals v naught over L times x. This is separable, and we have dx over x equals v naught over L times x dt, have this little extra x here, sorry about that. V naught over L times dt. And we can, if it's separable, we can just integrate from our initial conditions. So we are releasing the initial x position is x naught, and we are going to integrate it to some position x, dx over x equals, we're going to integrate from time, from the release time of the particle to the final time of the particle, some time t, times v naught over L times dt. And that's just constant, so we can yank that out of the integral. Okay, and we do this integral. It's fairly straightforward. And we have ln of x over x naught equals v naught over L times t minus t naught. Or x equals x naught e to the v naught over L times t minus t naught. Okay, and we would get the exact same result the standard way. So we get the same result the standard way. Okay, and I'll just show that. We have the integral of dx over x. Here we don't put the explicit bounds on the integral. Instead, we just add the constant to the side. Equals the integral of v naught over L dt. And plus some constant. I'll call that C1. So this implies that the natural logarithm of x equals v naught over L times t plus our integration constant, or exponentiating both sides, x equals e to the c1, which is just a constant, and I'll call that c2, times e to the v naught over L times t, and this equals c2, which is our new constant, times e to the v naught over L times t, and that equals x. So now we need to find c2. Well, we can apply the initial condition that x equals x naught at the release time t naught. Oops. Let me rewrite that again. That x at time t naught equals x naught. Okay, and so if you go through the standard procedure where you have x naught equals some c2 e to the v naught over L times t naught and solve for c2, you'll find that x equals x naught e to the v naught over L times t minus t naught. Same as above. Okay, and you can do this trick here if the differential equation is separable. You cannot do it for any other differential equation. Okay, and then for the y equation, let me underline this. So we have our generic x equation here. For y equation, we solve the ODE, and we have y equals y naught. I'm not going to go through it in detail. Equals e to the minus v naught over L times t minus t naught. Okay, and so here, these are the solution to the ODE. Notice we have not made any assumptions as to where we are releasing the particle. We've made no assumptions as to the final time. And we've made no assumptions as to the release time of the particles. So we have a generic solution, solution to find pathlines, timelines, and streaklines. Okay, and then to find one or the other, it's just dependent on basically which variables, basically which parameter we vary and which ones we hold constant. Okay, and then for pathlines, you pick t naught, the release time x naught, and y naught, and plot x of t and y of t on an xy diagram. Okay, now in this case the solution is quite simple, so you can actually eliminate time, and I'll do that right here. And so we have x equals x naught e to the v naught over L times t minus t naught, which is 0 because the release time is 0. This is, we want the path line, and so we pick t naught equals 0. And we have y equals y naught e to the minus v naught over L times t minus t naught. Again, we are releasing the particle at time equals to 0, so t naught is 0. And so this implies that x for our path line is equal to x naught e to the t, and y equals y naught e to the t. And recall that v naught over L is equal to 1 over is equal to 1 over s in terms of units. Okay, or is this equal to 1? Okay, now we can plot this in two ways. One, we can plot x. We can do a parametric plot where we plot x and y parameterized by time, and this should be minus t. Sorry about that. Okay, and or we can eliminate time and then get y as a function of x. So we can eliminate time t. So we solve for e of t. So we have e of t. We pick one of them. We'll just pick x equals x over x naught. Or e to the minus t equals y over y naught. And so why did I do that? Oops, or e to the minus t, sorry about that, equals x naught over x. So why did I do that? Well, now we have e to the minus t in terms of x and x naught. We can take that and stuff that into our y equation here. So subbing into y equation, we have y equals y naught e to the minus t equals y naught x naught over x. Okay, or xy equals x naught y naught. Same as streamline. Okay, so it was the same result as the streamline. And then for streaklines, you pick time t, which is the final stopping time, say 1 second, and you pick a release point, and then you plot y, or x, as a function of the release time, and y as a function of the release time. Okay, and so basically for the path line, we were plotting x as a function of time, and for the streak line, we were plotting x as a function, x and y as a function of its release time. But because the flow is steady, you can go through the same elimination procedure okay, and I'm gonna move this out of the way. You can go through the same elimination procedure to find that the equation for the streak line is xy equals x naught, y naught. Okay, and so how I got to there, so let's choose x equals x naught, e to the v naught over L times t minus t naught. Well, here we are varying the release time and we're picking a fixed t naught, so I'm just going to pick 1 second, and this v naught over L equals 1 over s to the minus 1. Okay, so this equals x naught e to the 1 minus e to the 1 minus the release time. And similarly, we can go do the same thing for y, and that equals equals y naught e to the minus 1 minus the initial release time, because here we picked a final time of 1 second. Okay, and I'm sorry about the handwriting, guys. I'm getting used to writing on this iPad again, all over again. But if you go through the same elimination thing, we have an e to the 1 minus t naught here and an e to the minus 1 minus t naught here. You can eliminate e to the 1 minus t naught like we did last time, and when you do that, you find that for the streak line, x times y equals x naught y naught, just like before. Okay, and so we've proven that for a steady flow that the streamlines, path lines, and streak lines are all the same. Now, how about the timeline? Well, how do we do that? Well, for the timeline, we pick t naught and t, and we plot the position of the particle at a given time t as a function of the initial position of the particles. Okay, and so if we do that for this example, what we find is that if we pick our initial particles to lie along this time, and I will do it like this. So we have a little red particle here, a green particle here, and a blue particle here. Okay, and so we have this array of 5 different particles, and we basically release them and let them move with the flow. Like this. Okay, and then we connect the dots between all of these particles. So this is the timeline at t equals to 0 timeline, and it turns out that that the particles just move horizontally and either up or down. So this is the timeline at some later time, the timeline at a time after that, the timeline at a time after that, and the final timeline. Okay, and so that's how. And so for this class, that's really all we're going to do with path lines, timelines, and streak lines. And you will have some homework problems on this stuff. And so that is it.